Let's do a quick review on the quiz and homework. Starting with a quiz. So you want to simplify this first. This one is ABE or CDE or AB, and which is AB 1 or E, because you can combine these two, or CDE. So this becomes 1. It ends up with AB or CDE. It's an unlogic, so you are getting AB in parallel. And then CDE in parallel as well. And then in series, right? AB in series and CDE in series. Oh. One, two, three, four, five. Two in parallel, three in parallel, and then in series. How do we do that? So two in parallel. And then three in parallel. Okay, do this. Does that work? So two in parallel and then merge to here. Merge to here, and then it's 1, 2, 3, and merged to the power supply, which is wrong. So this won't work. So how do you fix it? Just do not connect them to the power supply, right? Connect them down here. Is that correct? Still not correct? Really? So 1, 2, 3, and merge at one point. It's right. I think this is correct. Works. The only issue is you got metal. If you are using metal one for all these traces, you have to find either metal tool or is there a better design? I think I attached the solution to this one. Did I attach the solution? Yes, I did. So this is probably, I also stapled that solution to the back of your homework, okay? So let's look at this one. Oh, that's not a quiz. So I don't have a solution for the quiz for now. But I mean, this is fine, right? This is okay, this works. And then 1, 2, 3, 4, 5, 6 for the NMOS. That's easier. And that's it. So you got A, B. Which one is A, which is B? I will say this is A, this is B. Because this must be A, this must be B. And C, D, E. C, D, E. Okay, that's how to do it to get the full credit. So now let's look at this one, see if there's a better option. If we do the parallel from the top, so we can get rid of this intersection between these two traces. Just the top part, trying to optimize it. 1, 2, 3, 4, 5, 6. So now you'll see the benefit of doing stick diagrams, right? Before you lay it out in electrical VLSI, you can actually pre-design it before you do anything there to optimize the traces. 1, 2, 3, 4, 5. So I got 2 in parallel. If I introduce the traces here and get 1, so still there's 2 transistors in parallel. And then I'm going to do the 3 transistors in parallel. Can I do that for these 3? For CDE? Probably not, because this is being occupied already. Because none of the C, D, or E is being shorted to the power supply. So this doesn't work. It has to be this. So the way to do that is you introduce a via here to drill a hole to the top layer, to a higher layer, to get a metal 2, and then make the connection. So metal 1, still metal 1 here, and then metal 2, and then drill a hole, drill a via to get the trace 1 layer down to short it to metal 1, and then short to this diffusion, or the N+. So I'm going to cover the semiconductor basics in this week, and probably 1 or 2 lectures next week as well, to understand what are these materials. Okay, so this won't work. Now the second one.
So for that first one,
Mm-hmm.
you have to do the second one. You have to do that, okay?
No, this doesn't work. You mean for here or here?
Yeah, the one before you have.
For this one? That's what I'm thinking of right now. So I didn't prepare a solution for this one, so this is maybe not optimized. But do you guys have another solution for it? What you think? I mean, let's try it one more time. 1, 2, 3, 4, 5, 6. So because this is definitely not feasible, right? We don't want to do that. So I have to do this. So introduce 1 line here and then here. Okay, that's a 2 parallel PMOSes. And then in series with the 3 parallel PMOSes from here. How do we do that to get rid of these intersections? So remember the 3 parallel transistors? How do we do that? Like this, right? It's a classic structure. That's how you make a 3 parallel transistors. So we can start the trace here and output here, or do it the other way, which will be equivalent. So how can we implement this one in here? So that one, wait, because that's a drain of the 2 PMOSes of the A and B, so we have to connect this one. You have to start from here. That's the top. That's this node. So if you do it like this, then problem solved. Here, yeah, it's just a one metal piece. It's the same node, like a metal wire. Every single piece, every single location on the one metal piece has the same potential. It's the same metal. All right, that's a better solution. But is this correct? Let's check, wait. 1, 2, 3, and merge. Yeah, so that's correct. All right. Now the second one, A, B, C, D, E, B, C. One, two, three, four, five, six, 7. It's a lot of transistors. So 2 in parallel first, and then 3 in parallel, and then 2 in parallel. I think we can do it. So 2 in parallel and then 3 in parallel is very similar to the first one. Right? So 2 in parallel and then 3 in parallel. So we'll just do this. Is that correct? And then 2 in parallel. How do we do that? We need these 2 in parallel. Is that correct? Am I losing anyone? Did you get the trick here? So 2 in parallel, you can do either this. Remember? You can do either this, that's 2 in parallel, or if you flip it, it's actually the same as this. That's 2 in parallel. So for 3 in parallel, it's simply just this. So I can do these 2 here, these 3 here, and then these 2 here. And I'm done for the top. Then bottom, 1, 2, 3, 4, 5, 6, 7, 8. So this will be easier. How to do that? Two in series. Yeah. So that's 2 in series for A and B. And then another 2 in series, which is B and C. And these 3 in series, which are C, D, E. So that's one branch, it's the same metal piece. And it's one branch, two branches, and the third branch. So merge to here, to the ground. Merge to the ground. Is that correct? I think so. And then when you are trying to optimize the signal lines, you do have different options. But based on the layout view right now, I prefer this to be A, this to be B. Because these 3 transistors are in parallel, it doesn't matter which is which. But because of the 3 transistors at the bottom are in series like this, so I prefer this to be C, this to be D, this to be E. So I can directly short them, right? All the gates. For these two, they are in parallel, so it doesn't matter for which one is which. But here matters, so I prefer this to be B, this to be C. Does that make sense? Any questions? So based on your reaction, I decided to give you guys another quiz regarding this on Wednesday, along with the subtractor circuit. You don't have to draw the CMOS level circuits, but you are supposed to draw the block diagrams. For example, a 2's complement subtractor. You can draw just a box, say that's the FA, that's a full adder, which is fine. And also for the either it's a XOR gate or a MUX, whatever, to implement that subtractor function using logic blocks. It's a very simple problem. But in addition to that, you'll have 2 more AOI logic circuits very similar to these ones. So it just needs some practice to repeat on this. Okay. So that's a quiz. And now the homework. So to clarify one more thing, there's a little confusion here. So that's the inverter, right? And the input is always being shorted to the gates. I want to short this one to here. And the drain here, you short the drain of the NMOS and the PMOS together, and the drain is the output. And the reason this one can invert the signal is because when you give a 1 here, the NMOS is off and the PMOS is on. So whenever this is on, it's going to pull this pin down to the ground, so we're getting a 0. If you have a 0 for the input, the NMOS is off, but the PMOS is on, so it's going to pull this point to the VDD, so you get a 1. That's why you can invert the signal. And when you draw the layout, very simple and straightforward. You have to introduce, and you want to place the MOSFET in this direction instead of rotating that by 90 degrees. Okay, don't do that. The reason I want to do this is super straightforward. You can directly show the two gates together. You got one signal line. And that's the signal line. And you want to short these together because it introduces VDD to this pin, and then here's the channel, and here's the drain, and channel, ground. So that's the input, and that's the output. So don't lose any points on this one in the future. This is the very, very starting point of doing the circuit design and also the layouts. So here's the question, here's the answer, so the solution for this one, done. Right? And for the second one, I got confused. You know, you just forgot after you have done all these complex CMOS circuits, you just forgot the easiest one. You just forgot this one. Remember, this is the starting point. If you look at the notes, as a first class when we introduced the AOI logic, as simply just a NAND gate. Right, just do a NAND gate. It's PMOS. And there's none of the signals need to be inverted because this will be A, not A naught. It's going to be A, and this will be B, and that's it. And that will be A, B naught. If you don't believe it, just plug in any of the numbers, just give some combinations of the two inputs and see if you are getting an A, B naught. Very simple. So that's a NAND gate. This is not AND. If you want to make an AND gate, you have to invert it. Right? But right now you are getting a NAND logic out of this guy. And the state diagram for this one is very simple as well. You can find out the solution in many of the notes. And this is just a NOR gate. Simply just a NOR gate, but nothing else. And this is the AND gate. So keep in mind, AND is not this. Remember the De Morgan's law in logic? So AB equals to A or B, or A or B equals to AB. Just split the bar, change the sign, or merge the bar, change the sign. Okay? Remember that one. So no, this is not correct. So AB, so how to do this one though? AB is A, you can just do a NAND gate and then invert it, right? I mean, I'm fine with that one. Or I don't know how we're going to do that. It's just making a simple thing complicated. But now let's see what's this one is going to give us, right? If you use a NOR gate, which is fine, but the signal, you have to label the signal correctly. So if you want to do it in this way, it's going to be a NOR gate, but signals are changed. So that will be A naught, B naught. So if you don't do that, which is fine, but you have to label them correctly. Or you can just directly make a NAND gate and then invert it. And just draw an inverter after it. Okay. Now for the next one. Next one. NOR, so which means these two are in series on the top, and then C and D as well, and then E. So AB are in parallel, and CD. Oh, almost, sorry. So A, B, C, D, E. Oh. 5. How to do that? Because 1, 2, 3, and merge. For the following ones, 1, 2, 3, 4, 5, 6. Two in parallel, and 1. How to do that? So here's the output, right? You want to connect this one to somewhere, but we can do this one first. So I'm going to draw here first instead of messing up with this circuit. So 2 in parallel, so I can do this, and then 2 in parallel again. And then it doesn't work because this one, which is E, is not being shorted to here. I have to change the strategy, right? So what you want to do is probably like this, 2 in parallel output. That's the solution, how we do it. So this is what I did. The top one is easy, but for the bottom one, so I did this, and then, oh, so it goes through E first, because you can just swap these two, right? So you can put this one at the top, and this two at the bottom, which is equivalent. It's not going to change the logic. We'll replace this part. Because right now it's difficult to get the stick diagram done. So we have to change this one to E and CD to make it easier to lay it out. So what happens is I did this So these guys are A and B, and directly connect to E in series. And here's the output from E. And then I got two parallel transistors. Right? It's very helpful to have stick diagrams available to you guys before you lay it out physically. Okay. So the next one, yeah, this looks like easier, a lot easier. F. Yeah, that's easy. I don't have to go through that, I guess. I also have a solution attached to the homework you turn in. G is A, B, or C. Yeah, for this one, before we get started, have to convert everything into something bar, right? Put everything underneath the bar. How to do that? So use De Morgan's law. So this has been, the bar has been split and the sign has been changed. You want to put it back. So this one equals to A, B, or C, or D. And now it's easy. Let's do it very quickly. So in that case, I prefer this to be A, this to be B. So this must be A, this must be B. C, D in the order because these are in series. So I prefer, this must be C, this must be D. In that case, I prefer this to be C, this to be D. That's for G. H. That's a joke, right? Yeah, I mean, whatever you put in there, just like do this, I'm fine with it. You have A and B. All right, this makes no sense. It's just a joke. All right, we're done with the review of the homework and quiz. Have any other questions? Are we ready for the quiz on Wednesday? Again? Great. Practice more after the class, right? You just don't know how amazing it's gonna be if you repeat doing one thing. Not mentioning too long. I mean, just keep doing that thing for a month. You'll see a lot of difference. I bought a pull-up bar in probably September the 1st, and I can only do like 6 to 7 pull-ups. So I keep doing that for a month, and right now I can do 20. 30 days. Oh yeah, one more comment on graduation, find a job. I just recently found out students are still not prepared to get a job after they graduate. No matter how many examples they have practiced on during the college, it's very clear, right? For now, it's super clear. It's not like I don't know what to do to get a job. Do you know what to do to get a job? It's very clear. I mean, it depends on which path you want to follow, right? If you want to do computer engineering, I mean, more hardware or digital design, just do IPGAs. That's it. Take CE433 IPGAs. And if you want to get a job, probably just practice on the all these examples online. You can find out online. Just get an IPGA board. You can check out one board for me, or you can just buy one for yourself. And then buy a little logic analyzer. I just purchased 40 of them. If you want to check out one, just let me know. And just do IPGA. And there's a super high demand on the market who are looking for IPGA engineers. It's actually ASIC engineers. You just need to know how to program in Verilog, okay, to find a job. Or if you are willing to do microcontrollers, you want to follow the road of doing real-time system, not just Arduino programming. Any of the 32-bit microcontrollers like the ESP32 or the ST32, all these microcontrollers, and use FreeRTOS. So we don't want to just simply program one simple loop, because the microcontrollers in the industry, they manage different tasks at the same time. So you have to schedule it. The way you can schedule it, use a real-time operating system. So it's not Windows, not Linux, it's operating system being used in the microcontroller. You have to have a high-end microcontroller which has enough room in RAM to hold that operating system to schedule all the events. There are tons of tutorials online. Just buy one 32-bit microcontroller and find a job. If you search for embedded systems jobs, positions, there are hundreds of positions available in Colorado only. I mean, not mention Silicon Valley. There are thousands of jobs around. Depends on what you want to do, right? You have to focus. So that's the first one. Second one, IPGAs. Third one, just software, right? Algorithms. Like I just mentioned, right? Repeat. If you keep doing one thing for a month, I started with 8 pull-ups, and now I can do 20, just 1 month, 30 days. If you practice with the algorithm on LeetCode, normally people have recommended just keep doing that for 6 months, and you'll pass the interview at Google and Facebook. And starting with $200,000, why not just repeat? So the students have worked with me. So this thought came from the recent experience with the 3 graduates from the C program. I mean, they all found a job. But I'm still thinking, like, if we can do a better job on this to prepare our students for the interview on the first day after they graduate or before they graduate, one semester before they graduate, right? They find a job. I mean, how can we do that? I think the key point is to focus. I definitely you sometimes you want to do a lot of different things. You have to do that because these are required in the curriculum. You have to experience all these things, but find out one you are most confident at and trying to focus on that one. I mean, if you having a difficult time to find out one, just let me know. We can talk about it. But I think just pick up one as soon as possible will be very beneficial to you. Either one is great. I mean, if you need more money and you don't worry about just sitting there for 10 hours, 12 hours a day, just coding, just pick up this one. Just do a software job. It's so sweet. I mean, just think about that. You can get 120 at least at the start, at the very beginning. So these two are pretty good as well. But if I rank it, so this will be number one, so number two is number three. The reason for the embedded systems, the market is shrinking in the US is because compared to the ASIC design at the bottom level, this is relatively easier, a relatively higher level. I mean, not down to the bottom, a little bit higher level, but easier. So they always contract the projects to the small companies overseas, like in China or India. And the cost will be way lower. And they don't have to hire a full-time embedded system engineer and pay them $130,000 a year just refreshing their software in the embedded system. They always just contract everything to China, and they'll get the product done. Looks like it's a U.S. company, but everything was done in China. They just the cost for everything probably is even less than the annual salary for that engineer to be hired in the U.S. So that's just a reality right now. That's why it's shrinking. But for ASIC design, I think most of the U.S. companies are still holding that IP, so it's difficult to replicate everything in a different place. So I think either this one or this one, top choice. This is also a very good choice. If you search, you will see a lot of jobs. So either one. I mean, either one. Just pick up one and focus on that. So let's look at the flatter. We have a little left over here to wrap up everything. And remember, if you go back to the notes, if you look at the notes we have, here I just directly print it out, save your time. That's the high-speed flatter you are going to deal with in the lab. And the logic expression here, S is A or B or CI. So CO is and now the layout, the stick diagrams. For S, how many transistors we have for S? 1, 2, 3, 4, 5, 6, 7. That's the longest we have had. All right. How do we implement this one? So first, 3 in parallel. So what I did is like this. So that's 3 in parallel. And then 3 in series and 1 in parallel. So how to do that from these 4 transistors? So I just shorted to here to let the current merge in the middle. I'm getting a trace as an output from here. Have to deal with metal 2, I guess. Have to drill a hole to the top. So what I did is do it here first, and then to the ground. These are these 3 transistors, and then I got 1 and 3 in parallel in series. So go through this one first, and then 3 in parallel, which will be this. Okay, so that's for S. For CO, this one. So definitely, this is just for S bar. And if you need S, you need an inverter just behind it, right? For this one. This doesn't include this one. So in the inverter here. And now let's do this. Still got 2 minutes. We'll get it done. Four. So I need a 5 diffusions. So I didn't do it at once, but I think you can do it at once. Do I have a better option somewhere? No, I didn't draw it down, but let's see if we can do it. AB in parallel. Oh, we need a 5 actually, right? 5. 2 in parallel first. And then 2 in series. Okay, yes, we can do it. 2 in parallel first. And 2 in series. And 1 in parallel to get this. And now the bottom. Two in series. It's very similar to this one. So it's going to be 2 in series. In series, and then 1 in series, and then 2 in parallel. Okay. So that's the slider. We're done with the adders. Any questions on anything? No, clear? But I'll scan the notes so be able to prepare for the quiz on Wednesday. I updated the website. If you couldn't see the updates, refresh the browser. Definitely check that out. See the plan for these recent weeks. Okay. See ya.